So we would like to talk about the dual space of a Banach space, which is a very, very important space. So let X be a Banach space. And we define its dual. So remember that in this study, we just look at real Banach space. Its dual, X prime. We would call it sometimes the dual space, to be the space of bounded linear maps from X to R. R is a complete space, so this is a Banach space. And if X star, it's very usual to denote the elements of this space by X star. We call them functional. So if X star belongs to X star, it is called the linear functional. And its norm, since it can be considered an operator, it's the supreme for all x's that have norm less than or equal to 1 of X star of X. Okay. Let's give a simple example. So so consider the Banach space L1. It's a space that we have already studied. And let AN and in N be a bounded sequence of real numbers. In fact, let's set its infinity norm, as we say, to be the supremum of the absolute values of its terms. Then we define X star from L1 to R with X star of a sequence that belongs to L1 to be the sum from n equals 1 to infinity of AN xn. So since the sequence AN is bounded and the series of xn's converges absolutely, this series converges absolutely. Moreover, if alpha is the infinity norm of this bounded sequence, then x star of xn in absolute value, which is the sum from n equals 1 to infinity of an xn in absolute value. This is less than or equal to the sum of absolute value. And since all the ans are less than or equal to alpha, this will be less than or equal to the sum from n equals 1 to infinity of alpha times xn, which is alpha times the sum from n equals 1 to infinity of xn. Then this is exactly the norm of xn. So this is alpha times the norm of xn, d1 norm, and this implies that x star belongs to the dual space. Not only that, but we can show that x star is the norm of x star is precisely this number alpha, meaning the supremum of all the terms of the sequence. So how can we do that? We have already shown that. So we have shown that x star is less than or equal to alpha, because remember, we proved that the value of the absolute value of the output of this functional at xn is less than or equal to alpha times the norm of xn, and the norm is of the functional is the infimum of all the numbers that satisfy this inequality. And now if we use the other characterization for the norm, then we have that the norm of this functional has to be greater than or equal than the value of the functional at the element en. So here en is the sequence that has everywhere zeros and 1 at the nth place, nth position. And this is exactly an in absolute value. So x star is greater than all the ans, which means that the norm of x star has to be greater than or equal to the supremum of all the ans for n in n, which means that x star, the norm of x star is greater than or equal to alpha. So do you see what is going on? X star is, the norm is less than or equal to alpha. It's also greater than or equal to alpha. So x star, the norm of x star is equal to alpha. One can show, and that's not hard at all, it can be shown that any functional on L1 is obtained this way. I.e., it corresponds to a bounded sequence of real numbers. And that its norm is the supremum of the absolute value of the terms of the sequence. So we will later see that for most Banach spaces, we want to be able to concretely characterize its dual, and that the study of the dual provides us with a very strong tool in understanding a given Banach space more intimately. And that's all. Thanks for watching.